So Unit 8 is all about solutions. Specifically, it's going to be mostly about aqueous solutions, which means what? Water. Okay, so they're going to be water-based solutions, which is kind of appropriate for today, right? Did you guys notice what it's like outside? It's sleeting. Yeah, pretty much. Right, so solutions can be defined as homogeneous mixtures, which means that they're going to look the same throughout, of two or more substances. The homogeneous part of the solution could be solids, could be liquids, could be gases. Okay. Usually we only think of liquids as being solutions. But there are other examples like alloys. Who knows what an alloy is? An alloy would be an example of a solid mixture, solid solution, and it would be several metals combined together. Okay. Usually we talk about the solvent. Solvent is a key term here. Solvent is going to be the substance that's present in the greatest amount. So with the alloy of 18 karat gold would be the solvent, because it's the thing with the most. For aqueous solutions, which we're going to spend most of the time talking about, for the most part, water's going to be our solvent. There are going to be a few key exceptions where water is not the greatest in abundance. Then the exact opposite of a solvent is a solute. Solute is the other stuff that's dissolved in the solvent. It might be one thing, it might be several things. In the case of gold, I think they've actually got two other metals in with gold, typically 18 karat gold. Mostly for our aqueous reactions, we're just going to have one other substance in it. Okay, we classify solutions into three different categories when we talk about them. One of them that we talk about is the kind called unsaturated. An example of an unsaturated solution is if you take a glass of water and you just put a pinch of salt in it and stir it up. Or maybe a pinch of sugar. Let's say a pinch of sugar. That sounds more tasty, right? So if you take a pinch of sugar and you put it into a cup of water, you've got an unsaturated solution. The way you know this is because an unsaturated solution, the definition is going to be a solution where it has not dissolved the maximum amount of solute. Or the way it's phrased here, a solution that has less than the maximum amount of solute that can be dissolved. You can prove that something's unsaturated by tossing another pinch in and seeing if it dissolves fully. If it doesn't dissolve fully, you'll see crystals at the bottom. And then you'll know that it's not unsaturated. To go along, we've got a second category that is saturated. A saturated solution is one where you have the maximum amount dissolved in it. So you keep adding pinches of sugar. Well, you start adding teaspoons of sugar, right? And you get it to dissolve in there. And that's going to represent a saturated solution. The way you know you've reached the saturation point is when you start seeing crystals stay at the bottom that won't dissolve. The definition of saturated is that it can't dissolve anymore. But there are ways to get things to dissolve more, to get solvents to dissolve more than they should be able to hold. Anyone who's made sweet tea knows this. You guys know how to make sweet tea? All right. You boil your water, you make your tea. While the water's still hot, you put sugar in it because hot water dissolves more than cold water does. Okay. Then you allow it to come back to a cool temperature. When it comes back to a cool temperature, you have what's called a supersaturated solution, because right at that moment, it has dissolved more sugar in it than it's supposed to at that temperature. Okay, so supersaturated solution is a solution that can contain greater amount of solute than needed to form a saturated solution. These kind of solutions tend to be unstable. It means that they can crystallize, and that the stuff that's dissolved in them will come out of solution at some point in time. So other things to know about. Water tends to be the most popular solvent. That's why we talk about aqueous solutions in chemistry, and that's what we're going to wind up spending most of our time with. So the next thing we have to talk about here is solubility rules. Hooray! All right. So you don't have to have it memorized right now, but basically the solubility rules talk about whether things will dissociate in water or dissolve in water. And actually the two words are different from each other. This has to do directly with the worksheet that I gave you guys. Okay. The handout? Mm-hmm. So as you read that worksheet, as you read the handout on solubility rules, it says things are soluble or insoluble. Okay. So that means that reasonable amounts are going to dissolve or not going to dissolve. Soluble things will not form solids on the bottom, whereas insoluble things will form solids on the bottom when you toss reasonable amounts in. So sugar is not on the list because the list that you guys have is full of ionic compounds. Sugar is covalent, so it's not actually on the list. But just for example, sugar tends to be soluble, a soluble covalent compound. Okay, because when you take a spoonful of sugar and put it in a glass of water, a reasonable amount, and you mix it up, do you get solids on the bottom? No. Okay, if you put unreasonable amounts, sure, everything's going to be insoluble. Okay, so the definition of solubility talks about reasonable amounts, and nobody's defined what that reasonable amount is. I'm going to suggest that if you're going to think in your head, think about a spoonful in a glass of water, for the most part. A spoonful of salt in a glass of water should all dissolve. So that's why sodium chloride winds up being an example of a soluble salt. K2SO4, potassium sulfates, is also soluble. Calcium chloride is another example. There's just several examples there. Let me start this. There are three possibilities for when something dissolves. And the solubility rules kind of imply what's going on. The first thing that's possible is called dissociation. Things that are listed as soluble on the solubility rules dissociate. Okay. Excuse me. So when an ionic substance dissolves in water, the solvent pulls individual ions from the crystal and solvates them. So you can see kind of here water is pulling apart the chloride part, the negative part of salt. And here, another part of the water is pulling apart the positive part, the sodium part of salt. And here we see the salt crystal, the large conglomeration of positive and negative repeating patterns. Okay. So because water is something called a polar molecule, it has poles to it, a positive pole and a negative pole. So the negative poles of water, the oxygens, are able to attack the positive part of the salt crystal. And the positive poles, the hydrogens, are able to attack and carry off the negative part of the salt crystal, the chloride part in this example. So associated with the word dissociation is the word electrolyte. Electrolytes are going to be substances that can dissociate into ions when dissolved in water. So they're going to be your soluble things that are on your solubility rules. Okay. Actually, what I should say is good electrolytes. Good electrolytes are going to be the things that are soluble, because it turns out that most ionic compounds will dissociate slightly in water. The ones that are listed as insoluble actually aren't totally insoluble. A tiny amount will dissolve, but not a heck of a lot. So they won't be good electrolytes, or what's called strong electrolytes. Actually, on the video, the electrolytes are the little ions that have come off it that have dissociated. So we've got positive electrolytes and a negative electrolyte here. They're going to be what allows an electric current to travel through water, because pure water doesn't actually conduct electricity. Okay, so the last thing that we've got here, the last definition, is non-electrolyte. A non-electrolyte is going to be something that may dissolve in water but does not dissociate. Covalent compounds do not dissociate. So covalent compounds are awesome non-electrolytes. And if we're talking about Gatorade, since we were just talking about it, sugar is in Gatorade, right? They put some kind of sugar, whether it's artificial or natural sugar. Sugar is a non-electrolyte. So when they put the sugar in there, it's not contributing to the electrolytes. It's contributing to the taste so that you want to drink the stuff. Exactly. Otherwise, it'd be just completely disgusting. We can do this. Check this out. All right. 14 minutes. We can do this. 13 minutes. Strong electrolytes. Strong electrolytes dissociate completely when dissolved in water. And check that out. We actually have a solvation equation. I don't have to go as fast as I thought we did. Okay. So a strong electrolyte dissociates completely. The reason why I know it dissociates completely is it says it's soluble on the solubility rules. Okay. So when we write a solvation equation, we take the salt in question. In this case, it's NaCl. We draw an arrow with H2O over the top. This is how we know it's a solvation equation because we're trying to dissolve it in water. And we show what happens on the right side. Since sodium chloride is soluble, according to the solubility rules, it's going to break down into its component ions, which is going to be 2 ions. It's going to be a positive ion and a negative ion. In this case, it's sodium ion and chloride ion. And we draw them as being aqueous because now they're in solution. Okay, before they were in the teaspoon. You put them in the cup of water, you stir it up, and now they're aqueous ions. Okay? They're going to be strong electrolytes, so they're going to turn a light bulb on real easy and real bright. Okay? A weak electrolyte is going to be something that says that it's insoluble on your solubility rules. Okay. So a weak electrolyte is going to dissociate just a small amount because it's not really truthful to say it's insoluble. It's only slightly soluble. It's the way we should actually talk about. And we write the solubility rule, the salvation equation, in a similar respect. But here's the thing. We don't draw a single arrow. We draw a double arrow instead when this happens so that we can show that it's going back and forth. There's actually a solid on the bottom and an aqueous component, and the aqueous component sometimes recrystallizes, and another part of the crystal decrystallizes and turns aqueous.